Hello everyone. Limits Unit, Subsection 5, Discontinuous Functions. Part 1, the formal rules of continuous functions. When we draw a function, it's clear if the function is continuous or not. Think of it this way. If you have to lift up your pencil while drawing the graph, the function is discontinuous. Okay? The formal definition of a continuous function is the limit as x approaches a of f of x equals f of a. Well, what this means, guys, is that the limit of f of x approaches a is the same as the function evaluated or solved for at a. Okay? So, hopefully this makes sense. Okay? It's kind of intuitive, okay? But for the above definition to actually work, three things have got to happen. The function has to be defined at a, so it has to work. So you substitute a into the function and it works. Okay? The limit as x approaches a exists. Okay? And that's from the left and from the right. Remember, they have to be the same. And then the limit as x approaches a of f of x has to equal f of a. That means that 1 equals 2. Okay? That's... Okay. Now, look at the title, guys. It says discontinuous functions. All right. In order for a function to be discontinuous, the function has to break at least one of those rules. Okay? The best way to show this is with piecewise functions, and they're new to us, right? We haven't done a lot of work with these things, so it's good that we can practice them a little bit more. All right. Examples. Are the following functions continuous or not? And there's only 3, so pretty straightforward. If so, where are they discontinuous, and which rules do they break? Now, what I've done for us is I have picked functions that are polynomials. Okay, now polynomials by their nature are all continuous. So if these functions, these piecewise functions, are going to be discontinuous, they're going to be discontinuous where the breaks are, where the joins are. Okay, so at these spots here. So what we're going to do first, everyone, is we're going to evaluate these functions at the breakpoints. Okay, so let's just do that really quick. So x cubed for x is less than or equal to 0. All right, so at 0, okay, so 0 cubed equals 0. Okay, awesome. So then x squared, okay, at 0, okay, well, 0 squared is 0, so 0 squared equals 0. Okay, that's the first one. And then x squared at 1, so 1 squared equals 1. Awesome. Okay, now we have this weird parabola. Okay, so we're going to evaluate that at 1. So 1 plus 2 times 1. Okay, well, that's 2. So 1 plus 2 equals 3. And then 1 squared is 1. So 1 plus 2 minus 1. Okay, so 1 plus 2 minus 1. Okay, so that equals 2. Oh, wait a second. So these functions, okay, so these two line up. Okay, so 0 and 0. But those two don't. Interesting. Okay, so that's going to break the rule somehow. All right, so or at least one of the rules. Now, which one does that break? If you have a look, okay, so the two functions at 1 aren't going to be the same. So the limit of this function of f of x, limit of f of x as x approaches 1, and look, if we go from 0 to 1, so that's approaching from the left, equals 1. Now the limit as x approaches 1 from the right of f of x is 2. Wait a sec, well, what that means is the limit as x approaches 1 of this f of x thing is undefined. Well, wait a sec, it has to be defined. The limit has to exist for this to be continuous. So this breaks rule 2. Okay, that this function, the limits don't work, okay, at x is 1. Now, if we have a quick sketch of this thing, we'll be able to see it really easy. But again, the whole point is for us to be able to figure it out without necessarily graphing all the time. All right. Okay, so let's just make a quick sketch. All right, so it is x cubed for x is less than 0. Okay, so that, remember, x cubed kind of looks like this graph. Okay, for less than 0, that's just this part. Okay, now remember, look at the sign. It's just less than. Okay, so there's technically an open circle here. Okay, now at x squared looks like this. Okay, so from 0 to 1, okay, so that's like this. 0 to 1 looks like that. There's spot 1, 1. So, and these ones are equal, so there are closed circles at the ends. Oh, look, see, x squared fills in that dot. So that's nice. So the first part is continuous. And we knew that because the endpoints lined up. All right, now this next one, 1 plus 2x minus x squared, at x equals 1, that's 2. Now remember, we're not allowed to equal that because of that sign. So we have an open circle at 1, 2. Oh, okay. And then this thing, because it's a negative x squared, that goes down like so. Now if you look, these 2 points don't line up, and we knew that from up here when we evaluated. See, up here, guys, right? 1 did not equal 2. So we can see that the limit as we approach 1 from the left and 1 from the right doesn't work. So the limit as f of x approaches 1 doesn't exist. We break rule 2, and this function is discontinuous. Wow, that's a lot of work. All right, B. Okay, we're going to do the same thing. We're going to evaluate at x equals 0. Okay, so x squared is 0 squared plus 1, so this guy is 1. At x equals 0, the function equals 0. Okay, so that's just 0. And then at 0, x squared minus 1, equals minus 1. Look, guys, this thing here, the endpoints don't line up at all. So the limit as x approaches 0 from the right and the left, okay, the limit doesn't exist. So the limit as x approaches 0, okay, well, the limit as x approaches 0 from the left equals 1. The limit as x approaches 0 from the right equals negative 1. Okay, so this one, the limit as x approaches 0, doesn't exist. So that's another rule 2. Breaks rule 2. Okay, and if you have a look, the function at x equals 0 equals 0. So even if the limit did exist, the function wouldn't equal it anyway. Anyways, it's a rule 2 breaker because the limit doesn't even exist, so it kind of supersedes the limit equaling the function. Okay, but let's have a look at what this looks like if we were to graph. Okay, so x squared plus 1, okay, looks like this. So plus 1, it's an open circle, and it kind of looks like that. Remember, guys, you can graph these on your calculator because this function looks like this. But we're only interested in this part of it. Okay, and we have an open circle at the dot because we can't actually equal 0. Okay, then at x equals 0, y equals 0, and that's a closed dot. Okay, and then x squared minus 1 looks like a parabola this way, but this time we're only interested in that part. Okay, so again, open circle at -1, and it goes like this. So quite clearly the limit as x approaches 0 from the left and 0 from the right doesn't exist. Okay, it breaks rule 2. Okay, C. Last one. So as x approach, or again, we're going to evaluate these at 2. So 2 plus 1 is 3. And when x equals 2, y equals 1. Oh, that's 1. So again, right here, guys, these endpoints don't line up. But let's have a look at what this looks like. Now, this function's a little bit different. X plus 1 is a graph that looks like this. It's a straight line. Oh, that's not a very good straight line. Okay, straight line through here. So 1, 2. So at x equals 2, we have a hole in the line, and then it carries on. Okay, when x equals 2, y equals 3-ish. Okay, remember, because we can't actually equal 2 there. Okay, so we have this hole, and then when x equals 2, y is 1. So in this case, as we approach 2 from the left, we approach 3. As we approach 2 from the right, we equal 3. So the limit as x approaches 2 of this f of x equals 3. See, this time the limit exists. So this one doesn't break rule 2. Rule 2 is fine. Okay, rule 1, the function evaluated at 2 equals 1. So rule 1 is fine. Okay, and then rule 2 is fine. But we can see that the limit as x approaches 2 is 3. The function evaluated, so f of 1 equals 1. And what we can see there is the two don't equal each other. So rule 3 is that f of a has to be the same as the limit as x approaches a. Right? They have to be the same, and they aren't. So this one breaks rule 3. Does that make sense? So we have a discontinuity at 2. We broke rule 3 for this one. Okay, thanks guys. Again, any questions, give me a call, give me a text, whatever you need. Thanks.